Hello, welcome. Hello. Hello. Hello, Ben. Hello, Alex. Hello, Eve. Perfect.
Good. Goedemiddag. Gaat u zitten. Please be seated. Dames en heren, ladies and gentlemen, geachte collega's, dear colleagues. Ik heet u van harte welkom op de openbare doctoraatsverdediging van Jonathan Dan en ik verklaar de zitting voor geopend. De heer Jonathan Dan, master ingénieur civiel biomédical van de Université Libre de Bruxelles, heeft aan de faculteit een proefschrift voorgelegd, handelend over Signal Processing Methods for Home Monitoring of People with Epilepsy with a Network of Wearable EEG Sensors. In het Nederlands, signaalverwerkingsmethoden voor thuismonitoring van mensen met epilepsie met een netwerk van draagbare EEG-sensoren. En dit tot het verkrijgen van de graad van dokter in de ingenieurswetenschappen. Hij zal dit proefschrift nu verdedigen. Ik vraag aan de kandidaat eerst een uiteenzetting van ongeveer 45 minuten te geven over zijn werk. Daarna zal er gelegenheid zijn tot het maken van opmerkingen en het stellen van vragen. Meneer Jonathan Dan, u geeft het woord. I now give the floor to Mr. Jonathan Dan.
Thank you. Dear jury members, dear colleagues, dear friends, dear audience, from across the world with some guests from America, from Switzerland, from France, and from the Netherlands. Dear audience also online, which should be able to hear me now. I will present today my thesis on signal processing methods for home monitoring of people with epilepsy with a network of wearable EEG sensors. So today we will be talking about epilepsy, and epilepsy is a brain disorder. The main clinical symptom of epilepsy are epileptic seizures. Seizures can happen unannounced, and they happen suddenly. And in people with epilepsy, they will happen multiple times throughout their lifetime. Epilepsy is the third most common neurological disease. It affects more than 50 million people across the globe. And the fact of having epilepsy puts you at greater risk of premature death. Here is an example of an atonic seizure. An atonic seizure is a seizure where the patient loses his muscle tone. As you can see, the seizure is brief, and the patient recovers from his seizure quite quickly. There are many different types of epilepsy, and the types of epilepsy depend on the location in the brain that is affected and of the seizure type. In some seizures, patients can become unconscious, can have involuntary muscle contractions. They could also have some visual hallucination or other sensory hallucinations. EEG is a brain disorder, and we're going to dive a bit into the brain to understand the mechanisms of the disease. So the brain is made of neurons. Neurons are excitable cells with long fibers that connect them to other neurons. This is a schematic representation of many neurons, and you can see that they are organized a bit in a forest connecting to many, many other neurons. Together, they form a large network that allows the brain to perform its computing tasks. The information that is carried in a neuron is an action potential. It is an electrical signal. And this electrical signal propagates along the axon of the neurons before reaching the axon terminal and liberating chemical neurotransmitters that will pass on the signal to following neurons. Epilepsy can have many different causes, and the causes of epilepsy are due to a malfunction either of the network or to one of the means of communication of neurons. And the disease can manifest at any age. It can manifest in newborns, could be due to genetic factors. It could manifest later, maybe through neurological infection, head injuries, brain tumors, maybe a stroke, and many, many other causes. To measure an epileptic seizure, we measure the electrical activity of the brain. And this is done using electroencephalography. Electroencephalography, that I will abbreviate throughout this presentation as EEG, is a recording method that records the electrical activity of the brain. It was first proposed already in the 1920s by an Austrian psychiatrist called Hans Berger. And I will now demonstrate the equipment that is needed to record an EEG. So to record an EEG, you place electrodes on the scalp of a subject. Here I have several electrodes placed on the scalp of this monkey, and the electrodes are here to establish an electrical connection between the scalp and between the recording apparatus. And then you can see that these electrodes are connected through wires to an EEG amplifier. The amplitude of EEG is very low, and so you need to amplify the signal to be able to acquire it. You then convert it to a digital signal and then transmit it through USB, for example, in this device, to a recording device that could be my computer. I will now show you a recording of EEG. And here is a recording that was performed not on this monkey, but that was previously recorded in a hospital setting. You see that I have multiple channels. These are these horizontal lines, and each channel corresponds to a measurement location. And I record this signal over time, and in a hospital setting, I would typically record it for, say, 20 to 30 minutes. What you can read in this recording is the electrical potential between two electrodes. And this difference of potential is very small. We're talking here about tens of microvolts. If I wanted to send this patient home, it would be quite difficult. I have too much equipment, which is connected to a computer, to mains, and is not a portable setting. Luckily, electronics have evolved, and it is now possible to do home EEG monitoring using wearable EEG sensors. And here is an example of such a small EEG amplifier. And so I'm now going to connect my monkey to this wireless EEG sensor, or to this portable EEG sensor. And with this portable system, I can now send him home to do long-term EEG monitoring. And this could, for example, last for, say, 24 hours. And if I record him for a long period of time, I have much more chance of recording an epileptic seizure, because seizures are rare events. And so let's start recording this monkey in a home environment. And if I record him in a home environment, I have much more data, and at one point, I will record an epileptic seizure. What you see here, the signal now evolving, is evolving into an epileptic seizure. This is a generalized absence seizure. We call it a generalized seizure because it affects all the brain, and you can see that all channels have got epileptic activity. And you see that this activity is very different from the background EEG activity. First of all, it is organized across the different channels, while usually EEG is very much disorganized between the different channels. And it has got a very characteristic spike and wave template that is repeating. The whole seizure lasts about 10 seconds, and for this type of seizure, the person would just be unaware of his surrounding for a brief period of time. In my thesis, we look at how can we miniaturize still further these wearable EEG systems. And to do that, we propose something different from what is currently done. In the system that I hooked up on the monkey, all EEG electrodes were still hooked to one central amplifier. What I envision is a wireless EEG sensor network. In a wireless EEG sensor network, you have many small nodes, such as the nodes that Bitewise develops and which I have here in my hand. Each node measures only a local EEG activity. And each node is thus not connected to the other nodes, or only wirelessly, and so you can remove all wires that you would have on the scalp. Each node only measuring a local activity has also got a short inter-electrode distance, which makes it a smaller node. And finally, in the setups that I would be using, we would limit the number of channels to make the setup more portable. To build a wireless EEG sensor network, you need a wireless EEG that has got several components. One of them is a miniaturized EEG amplifier. A second component is it needs to be able to communicate to other EEG nodes to obtain the signal across the different channels on the scalp. Finally, to reduce battery usage, we would need some of the processing to happen on the boards such that they could compress data and exchange relevant data between each other. If you have wearable EEG for home monitoring, you can do several things. You can improve diagnosis, and you can record seizures that would otherwise not have been recorded in a hospital environment. You can build accurate seizure diaries, where you would log the events and the seizures that a patient has over time. And you could imagine applications where you would have real-time alarms of epileptic seizures that would allow to call for help, or maybe even to deliver some seizure-aborting medication. In my thesis, I concentrate on the signal processing aspect. This means I am developing tools for EEG monitoring of people in their everyday life with a wireless EEG sensor network. And specifically, we'll be talking about three things. We'll be talking about automatic detection of epileptic activity. We will then talk about channel selection. Where do we place the electrodes or the nodes on the scalp of our monkey? And finally, we will be talking about miniaturization limits of such nodes. How close do you place the electrodes, and how many of these nodes do you place on the scalp? So let's start with the first topic, automatic epileptic activity detection. The task is from an EEG recording that you have to automatically know when you have an epileptic event. The reason you would want to do that is that long recordings of the EEG take a lot of time to analyze and are typically only analyzed by experts, neurophysiologists or neurophysiologists. The task of automatic epileptic seizure detection is to find an algorithm that will tell you, well, here, in this window highlighted in green, is an epileptic seizure. I'll first tell you how standard machine learning would do that. And what standard machine learning would do is it would first segment the signal. Segment the signal means it will analyze the signal in individual blocks, providing one label, is this window a seizure or not a seizure, for each window of data. To do that, on each window, it will do some feature extraction. And feature extraction means finding characteristics that describe this window in numbers. For example, what is the maximum amplitude of the signal in this window? What is the dominant frequency? What is the correlation of this window to either the previous window or the following window? Are there some entropy or nonlinear features that describe this signal? And so on. All these different features can be represented in a graph, and you can, for example, characterize this first window of an epileptic seizure with this green star. You would then do that for a following window, which is not a seizure, the example I have here, the next one, the following one, and you do that for many, many examples. Once you have many examples, you can train a classifier, you can train an algorithm, which will automatically perform the task of saying, well, is this new point that I'm investigating, is this an epileptic seizure or not? This whole process is computationally quite expensive. The feature extraction can be difficult to perform, at such that it would not be suitable to run real-time on one of these miniature nodes like I would use in a wireless EEG sensor network. The classifiers themselves often require a lot of memory of past examples to perform a new classification. So in this thesis, what I do is I propose another algorithm, another way of doing things to be able to do this automatic classification labeling of seizures, but on an algorithm that would be able to run on such a miniature EEG sensor. So let's go over the different steps of the algorithm, and we're going to explain this in steps. So it is based on filtering, and I'll start by explaining spatial filtering. So we acquired the EEG on different points of the scalp. What spatial filtering does is trying to find a combination of these different channels that will amplify the seizures and that will attenuate everything that is not a seizure. And to do that, we're going to do a weighted sum of the different EEG channels. In this example, I take the first channel 6 times, the second one 5 times, the third one 1 time, fourth one -3 times, and the last one 5 times. I multiply these signals and I sum them up, and I obtain this purple line. This is what the multiplication looks like, and you see that the third channel is very strongly attenuated, and the fourth one has got its polarity inverted, such that the spike that you have slightly after here, which is not a seizure, gets attenuated in the output signal. So what this spatial filtering did is it combined the different channels to enhance seizures and to reduce artifacts. This is spatial filtering. I can also do this in the time domain. In the time domain, I have one channel, and I'm going to multiply windows of this channel with a temporal filter. And so I'm going to multiply the EEG signal, which is in black, highlighted here in orange, with the orange signal. This is going to produce one output. And then I can run this multiplication over the full signal and obtain the output temporal filtered signal. I could also do a combination of spatial filtering and of temporal filtering, which I call spatial temporal filtering. That is actually what we use in my thesis. And what happens here is that each channel first get temporally filtered by a specific filter, and then they get combined to produce a filter output. I told you how you produce the filter output, and didn't really tell you how do you find the different coefficients in this filter and how do you find the optimal filter. To do that, you need to write some mathematics and you need to formalize the problem. And so we write something which is an optimization problem and which says that you need to find the filter coefficients that maximize the power of the filtered seizures relative to the power of the filtered noise. This procedure allows you to find the weight of the spatial temporal filter. And it so happens that the problem that I'm showing you here can be solved with linear algebra using generalized eigenvalue decomposition problems. So later on in this presentation, I will be referring to generalized eigenvalue decomposition problems because this is a problem that allows to find the filter weights. I told you how to find the filter weights. I didn't exactly say how we did the N classification. So you apply your spatial temporal filter and you obtain the filter output, this purple line. On this filter output, you can compute the power of the filtered output. This is represented here by the orange line. And then, if you apply a threshold on the power of the filtered output, or you can say that anything that falls above that threshold corresponds to an epileptic seizure, and anything that falls below does not correspond to an epileptic seizure. And you see here that the seizure would be detected, is highlighted here in green. I show here an event which is not an epileptic seizure, which is high power, but which gets very well filtered out by the spatial temporal filter, and which does not cause a false positive or a false detection. This is the algorithm I use, and we wanted to validate the algorithm. So to validate the algorithm, we set up a study with the University Hospital of Leuven, where we sent home patients with absence seizures. And we recorded them for 24 hours outside of the hospital in their daily life. Those were 24-hour recordings on 8 patients, and we recorded a total of 101 seizures. You see here the device that we used to do that monitoring. Several findings came out of it, all related to using this spatial temporal filter on these patients. The first one is, even though we had hooked up 21 electrodes on these patients, we found that the performance of our algorithm was equivalent if you used only 10 electrodes or if you used 21 electrodes. And so one of the messages was, well, you maybe do not need all the electrodes to perform an accurate seizure detection. You do need to choose them, and that will be the topic of the second chapter, but you do not need all of them. You could also choose to use less than 10 electrodes, but you know that when you start reducing, you are going to get some errors, some false detections, and then that is a choice. How many false detections do you allow compared to how much wearability and how much more comfort do you think you can get for the patient? Second finding was that the algorithm requires only very few examples of seizures to obtain a good classification. And this is quite different from the machine learning algorithms that I showed you to start with, where often you need a lot of data to train classifiers. I then compared the algorithm I was proposing with other algorithms that had been proposed for absence seizure detection in a mobile context. And I found that the algorithm I proposed actually performs as well, or nearly as well, as many of those. But the algorithm I propose requires way, way less computational power. And that is way less computation, both in terms of memory, how much memory is required on these wearable sensors to do the real-time detection, as well as number of operations for each new classification. That means that the algorithm I propose would be suitable to put on such a small wearable sensor and one in a real time. That concludes this first chapter. The second chapter relates to channel selection. The task of channel selection is to say you have an EEG headset where you have previously recorded many electrodes. You would like to send that patient home with only a few electrodes. How do you know which of these electrodes to choose and which one of these electrodes gives the best performance for a seizure detection task? And while the problem might sound simple, it is pretty difficult to compute. It is a problem of combinatorial complexity, which means that the task of selecting 10 channels out of 64, if I had to evaluate each one of the possible combinations of 10 out of 64, I would get this huge number of combinations. And this huge number of combinations, if I had to evaluate my seizure detection algorithm on each one of them, that would be 9.5 years of computation. It is something that cannot be done in the scope of this thesis, and so I needed another method to do the channel selection, which would not explore all the possibilities, but would still be able to guarantee that it was providing a good solution. I'll start by explaining two more simple algorithms called the forward selection and the backward elimination. And to explain them, I'll give you an analogy. Today, we need to form a team of 3 players to play football out of these 5 animals. And we'll start by doing what the forward selection algorithm would do if it had to form the best team. The forward selection would first evaluate individually the ability to play football of each one of these players. So it would find that the teddy bear has got a score of 3, the giraffe of 5, the squirrel of 2, the fox of 8, and the bird of 6. And what the forward selection would do is it would select the best animal to play football. In our algorithm, that would mean selecting the best channel to discriminate between epileptic seizures and events which are not epileptic seizures. In the first iteration of our algorithm, you select the best animal. In the second iteration, you say, well, let's find the best pair of players that includes this first animal that we selected. And in this example, it would select a pair of the fox and the giraffe. In the third iteration, it would select the best 3 players that include the fox and the giraffe. And in this example, it would select the combination of fox, giraffe, and squirrel. But you can very well imagine that the fox is a really good individual player, but a terrible team player, such that putting him in a team with other animals is by far not the optimal combination. You can do this process in the reverse direction. That is called the backward elimination. You form the teams of 4, and you select the best team of 4, thus eliminating one of the animals. You are just left with 4 animals for the next iteration of the algorithm. And in a similar fashion, you could imagine that the bird is very shy when playing in a large team and doesn't contribute much, but in smaller teams is a very good team player. So I developed an algorithm which is not constrained by previous choices that it made at previous iterations, and is able to find a solution which is closer to the optimal solution. The algorithm I designed is a convex optimization formulation for group-sparse channel selection of generalized eigenvalue decomposition problems. So let's decompose what this means. We're talking about convex problems. Convex problems are problems which have got only one global solution, which means that when you run this algorithm several times, you are always going to find the same solution, which is the best solution to this convex problem. Group sparse refers to the fact that when we deselect one of the EEG channels, we deselect all the filter coefficients associated with that channel. It is the notion that we are not just selecting filter weights, but that the filter weights have got a notion of group and know that they belong to a channel, which is a characteristic that we need for our problem. And when I say for generalized eigenvalue decomposition problems, well, that is how I find the filter weights of my spatial temporal filter. And so this is a problem that is going to find both the optimal spatial temporal filter weights as well as constrain the number of channels. To evaluate this, I use Monte Carlo simulations. Monte Carlo simulations are simulations where I run hundreds and hundreds of different configurations of simulations of epileptic seizures and simulations of events that are not epileptic seizures. And on each one of these configurations, I run all the different channel selection algorithms to compare them. And the first thing I found was that the proposed method outperforms all other methods for this type of problem, especially when selecting a low number of channels. Second thing I found is I found a specific failure case of the backward elimination. And I proposed a modification for this method that allowed it to be way more robust. And the forward selection and backward elimination do have some characteristics which are appealing to use in that they require way less computational power to find a solution than these convex optimization problems. This concludes the second contribution, and the third contribution relates to miniaturization limits of wireless EEG sensor networks. In this study, I had access to recordings of high-density EEG. High-density EEG places many, many electrodes on the scalp, 257 in this study. What this allows me to do, it allows me to emulate short distances of my nodes. I have so many of these electrodes placed on the scalp that if I only use several of these electrodes which have got a fixed inter-electrode distance, I can emulate my miniaturized wireless EEG sensor networks. So I could evaluate two things. What is the impact of the inter-electrode distance? And what is the impact of the number of EEG units on the activity of epileptic activity detection? The activity that I was monitoring here was not epileptic seizures like I did in the past, but are interictal epileptiform discharges. These are spikes of epileptic activity that occur in people with epilepsy between their seizures. Here's an example of a spike. These spikes are very short events that stand out from the background. The procedure I would do is I would build a pool of candidates that all had the same fixed inter-electrode distance. Out of this large pool of 250-something possible combinations, I would then run a channel selection algorithm to only select 1 to 10 channels. On each one of them, I would evaluate the ability of my epileptic spike detection algorithm, which was the same algorithm as was proposed to do absence seizure detections. And what I would do is I would compare the performance of the algorithm when it was running on this wireless EEG sensor network compared to the algorithm when it was running in a clinical setup, so where you had access to 20 electrodes that all had a long distance. I found several things. The first thing I found is that the amplitude of these spikes decreases with decreasing inter-electrode distance. And this, I suppose, would be expected, is that when you start measuring closer and closer electrodes, you're measuring more and more local electric fields, and these activity will have lower amplitude. I could also quantify it, and quantifying it is useful when you want to design a device that would have to measure an epileptic spike. And what did I find? Is I found that at 2 centimeters, an inter-electrode distance of 2 centimeters, the average spike power is 4 microvolts. And 4 microvolts is low. Current EEG devices, or at least used for hospital settings, often have a sensitivity of 1 microvolt, which means that you're very close to the noise floor and that you will probably not be measuring that spike very accurately when you do it at short distances. And which probably means that if you wanted to design an amplifier to measure at short inter-electrode distance, you might want to increase the accuracy of your amplifier. I saw that contrary to the amplitude, the signal-to-noise ratio remained fairly constant. And that indicates that the spike is still present in the signal. You just need to be able to acquire it. The second finding I had was related to the ability of the spike detector compared to the ability of a spike detector used in a clinical setup. And the first thing I found is that if you increase the inter-electrode distance, you increase the agreement between the wireless EEG sensor network and between the hospital conditions. Second thing I found is that if you increase the number of nodes in this wireless EEG sensor network, you also increase the agreement with the clinical setting. And specifically, if you use an inter-electrode distance of 8 centimeters, and that you only use 2 nodes in your wireless EEG sensor network, you get to agreements between the clinical system and between the wireless EEG system, which are very comparable to what humans have got in terms of agreement when you ask 2 humans to annotate a file for intrictal epileptiform discharges. If you decrease the distance to 2 centimeters, you need at least 4 nodes in your wireless EEG sensor network to obtain the same level of agreement. This concludes the findings of the third chapter, and we can now draw some overall conclusions of the work presented in this thesis. So what this thesis did is it contributed to the development of wireless EEG sensor network to monitor people with epilepsy in a home environment. And specifically, it brought 3 contributions: the development and the validation of an algorithm for automatic epileptic activity detection that is well suited to run on a wireless EEG sensor network. It also provided a new channel selection algorithm, and it also improved 2 existing channel selection algorithms. And that chapter also provided a benchmark with existing channel selection algorithms that allow future researchers or future people using channel selection algorithms to know which algorithm to use in their specific conditions. The third thing it did an analysis of the limits of miniaturization of wireless EEG sensor networks and was able to provide some guidelines on the number of nodes and of the inter-electrode distances that would be required to detect epileptic spikes in a home environment. There's, however, more work that should be done in the field to further improve the quality of recordings in home wearable EEG. And one thing is, the algorithms I developed, I only tested them on absence seizures and interictal epileptiform discharges. And there are ideas and suggestions in this thesis of future work that could be done to these algorithms to tackle more seizure types, such as focal seizures, which are more difficult to detect than these generalized absence seizures. In the future, we would also want these algorithms to have an evolving mechanism. In the way I train and apply these filters, they are trained on pre-recorded data and then just applied. But you can very well imagine that if you were in a home environment, the characteristics of the signal might evolve over time. That might be due to one electrode coming loose or to other changes in the EEG signal. So you would want to propose modifications of the algorithm that allowed it to adapt over time. Certainly, in this work, I only concentrated on algorithm development, but other components are also required to do home EEG monitoring, and some of those are further improvements to the electrodes to do long-term EEG monitoring. That concludes the presentation I wanted to give you, and I welcome any questions and discussion on the thesis.
Thank you. Before we start with the second part of this defense, which are the questions and the comments from the members of the examination committee, I would like to introduce the different members of the committee to you. There are three supervisors to this work. There's Professor Alex Bertrand from the Electrical Engineering Department. There is also Professor Van den Driessen from the company Byteflies in Antwerp and New York. And there is Professor Van Paassen from the Faculty of Medicine at our university. And then, unfortunately, we have two members who are absent today. One of them is online, and that's Professor Jonas Dun Henriksen. He's online from Denmark. He's at the company UNEEG. Is he online? That's fine. Then we also have Professor Atienza from the University École Polytechnique Fédérale de Lausanne, who unfortunately had a car accident some weeks ago and who cannot attend. I think he's watching us on the streaming, but we're not sure. Okay, who is here then? Well, we have Professor Sabine van Huffel from Electrical Engineering at our university, and also Professor Michael Kraft. They both are there. Finally, my name is Yves Willems. I'm chairing this committee as a former dean of the faculty. So the questions that Professor Atienza sent us will be asked by one of the promoters, by Professor Bertrand. And the questions from Professor Dun Henriksen from Denmark will come online, we hope. And he will be the first one to ask questions.
Hi, Jonathan. How is the sound?
It's perfect.
Very good.
Very good. Okay, thank you so much for the presentation again, I can say. So a few questions on my side. You didn't show figure 2.5 in your presentation, but just for the audience to describe it, it's a view over the median over the different subjects of seizure false positives per day when setting the sensitivity to 95% and varying the number of channels in and time lags. Yeah, I think it's really good that you're looking it up. So here you can see how the false positive rate changes depending on the channels and the number of time lags. But what I notice on this figure is that you're not really reaching a minimum. You could easily have turned up the number of time lags L. Why haven't you explored that any further?
Yeah, the number of time lags could have been increased. So what you're trying to do is you're trying to build a system to run on a wireless EEG sensor network. And so what you know is that you do have some constraints on how much computing you can do. Those constraints, or the computing power of these algorithms, or computing resources required by the algorithms, are directly linked to both the number of channels and the number of time lags. So while you could theoretically increase the number of time lags to infinity, that would be something that would not be feasible in a wireless EEG sensor network. And so in this work, we stopped at 25 time lags, which corresponds to 0.5 seconds. This is an arbitrary choice, and it might have been interesting to also investigate what happens if you looked at 2 seconds of retrospective data or more. There's something you do need to realize is that all of this is trained on examples, and on these examples, you do build a filter. And there is some redundancy in the data when you start to include time lags. The seizures start to resemble each other when you start taking more time lags. And at one point, you can reach overfitting problems that you would find in other type of machine learning algorithms. So in this work, the overfitting in that the number of time lags you have available, the number of lags you have available in total, is close to the number of examples that you have, and you can perfectly distinguish between these examples of seizures and these examples of non-seizures on your training set. So to combat that, in the text, there was also a regularization scheme that was proposed, such that you don't have too many problems with redundancy of the data and with overfitting. It does remain a problem, so there will be limits to how much a static algorithm, which is not evolving over time, can be better at distinguishing known examples of epileptic seizures to unknown examples that will pop later. And so having something that has got slightly less filter time lags, but that is more generic for this type of seizure, might actually increase detection performance on the test data set.
Okay, yeah, I think that's fair argumentation. According to the figure, we didn't see the change in the curve at least, and my follow-up question would be if you, because I perfectly buy your idea that this should be feasible to compute on a small microcomputer. But if you reduce the number of channels, let's say you're not looking at 10, but only looking at 5, then you could, on the other hand, increase the L. Yeah, that's completely correct, and it's even more true if you were limiting to, let's say, 1 channel or to very few number of channels, like other systems have proposed. Right. Okay. So I know we are limited in time here, so I only have one more question for you. Now I want to put on my if I were Byteflies, the company you've done this in collaboration with,
hypothetically.
Ask you, how many channels should we include in our next generation product?
So that very much depends on the task, right? And so what we showed is that it's going to be a different number if you're doing spike detection and that you know the spike onset zone, that is going to be absence seizure detections, that it's going to be focal seizure detections, or even depending on what you want to use those detections for. And so I'm not going to give you a definite answer. I am going to say, if you want to do seizure alarms, I do believe that you want to have a very low number of false alarms. But on the other hand, you probably do want to wear the device for very long periods of time, and you are going to fall in the ballpark range of, I don't know, 5, 6, around those number of channels, I suspect. I suspect that if you're just doing detection, and that you just want to be able to have a seizure log, but that you can allow a human to then review the data and maybe use more powerful algorithms than the algorithms that I use, which are specifically meant to run real time, then you can get away with way less channels. And then 1, 2, maybe 3 well-placed channels would be sufficient for the task of home monitoring if the goal was to build a seizure diary. So it's not a black and white question, and it very much depends on both the type of patient and the task that you're trying to perform.
Okay, very clear. Thank you very much, Jonathan. That's all from me.
Next is Professor Sabine van Huffel, and I'll give her the microphone. You have?
I hope so.
Oh, Alex will need it. You just keep it.
Okay, thank you for your nice presentation, which is very optimistic, I would say, for for epileptic seizure detection. Okay, for absence epilepsy detection, it's in fact, yeah, this can be feasible, but for the other types of epilepsy, I still guess there's still a lot of work to do, as you also have in your conclusions. The questions I have is in chapter 3 on the selection for the grouped selection, grouped variable selection to find the optimal sensor setting. And I want to go to your real-world data example, especially figure 351, where you show, in fact, that the backward error method is worse if you decrease the number of channels selected. And I just wonder, because I don't see it in the text, whether you used any type of regularization in that figure.
No, so in that figure, that was the, let's say, naive implementation of the backward elimination, which does not use any regularization scheme. Okay. And in that, when you don't use them, you do see that for a very low number of channels, the backward elimination is, so to say, stuck with the previous choices it made and can get to suboptimal performance. That is why we actually did propose a general regularization scheme. Yeah.
Can you then repeat your conclusion if we can use regularized backward elimination, as you did, in fact, on the pages before, because this will also change the conclusions here. Can you expect how the figure will lie in that? Will it be it will be outperform the forward selection method and also the method that you propose here?
Yeah. So this is a real-world data example, so it's not very large Monte Carlo simulation. So it is a bit difficult to say in this particular example what would happen to the algorithm. So it's a bit easier to answer in the case of many simulations. The backward elimination always does suffer from the fact that the choices it makes are irreversible. So even though regularization does help it not make very bad choices, it doesn't completely eliminate the problem. And so what you typically would see is you would see the forward selection and the method we proposed that for a very low number of channels, let's say 1 or 2 or maybe even 3 channels selected, would still outperform the regularized backward elimination. But you would see that decrease change. You would see it reduce compared to what you have without the regularization.
Okay. Okay. Assume that you selected 2 or 3 channels, as you did here, because it's really the real-world example for absences. So the channels that you selected, were they also meaningful in the medical context? Because I don't see which channels you selected.
Indeed.
But
so
they should, of course, be relevant for absences.
Indeed. So we had started a preliminary study where we had checked if that could be used in a clinical setting. And we had stopped that study when we found that actually doctors did at least as well as our algorithms and that there was no real added value to the choices of the algorithms compared to the choices that Professor Van Paschen would make. What it found is that for generalized absence seizures, you often can't really get it wrong. About wherever you place the sensors, you will be detecting it, and the task of absence seizure detection, as you know, is relatively simple, and so you will still be able to get good scores of detection practically wherever you choose. What you do see is that there's a slight predominance of the frontal channels which are selected. And this does make physiological sense.
And did your solution also select these frontal channels?
Yeah, so exactly. So overall, if you sum up all the selections, there were slightly more selections that were made frontally than they were for the other channels, but that is quite slight. I could show you some figures. What we also found is that for focal seizures or for the spikes, the channels selected are very much around the seizure onset zone.
Okay. Then I want to move to chapter 4. This is also a smaller question about the metric that you used in equation 4.2. Let me see. So it's a distance metric. Yeah. This magic formula that you use to find the value or the parameter p. It depends, in fact, on the orientation, v1 times v2, but then it's preceded by an exponential, and you take then minus 2/3 of the distance. So where is this formula coming from?
So there are several aspects to it. So what the formula does is it's trying to establish what is the distance between electrodes and what are close by electrodes. And specifically saying that we want to remove some redundant channels which are very close by. There are two components to redundancy. One of the redundancy is to be geographically close, spatially close. And that we do along a sphere. So we model the head as being a sphere just because geometrically it makes computation more easy. Always a model that can be used. And the second component is indeed the orientation of these channels. And that is because two channels which are parallel will be recording very much the same EEG activity, and two channels which are perpendicular will be measuring a different electrical field. So that's that aspect of it. The last aspect is the exponent, and the exact value of the exponent is not important. We wanted an exponential decay to say that you penalize sensors which are far away compared to sensors which are close by. Why 2/3? For no good reason, and it would work perfectly well if you used half or if you used 1. If you used another value.
And is this your formula that you invented?
It is indeed my formula that I'm using, which is using two parts of the intuition. One is to say you need to be geographically far apart, and the other one that you need to have orientations which are different.
Okay, thank you. And then I have one general question. Well, we have been working with biteflies for years, I guess. So I really guess, or I really would like to know, in fact, how your work that you had here contribute to optimize the channel selection using the biteflies sensor dots that you're also showing. So can you say a few words about that?
Definitely. So the work that I did here is only based on the quality of the signal. These are the only metrics that I've been using throughout, which is to say how well can you distinguish between epileptic activity and non-epileptic activity. That is how I formed the selection. Biteflies is now at a stage where they are actually measuring people with epilepsy in a home environment on practically a weekly basis. In those patients, there are other constraints that come into account, for example, related to wearability, comfort, and ease of use of those subjects. And so what my work does is it provides to biteflies some indications to tell them, well, the locations you're using are adequate, would be overperformed by another location, and then the design choices are something else, which are separated from my work, which is really related to signal quality. So I see my work as providing biteflies with tools to be able to evaluate what is the impact of the locations that we are using compared to other locations that might be selected by an algorithm.
Okay, thank you very much.
Yeah. Jonathan, thank you very much for this very nice presentation. It was very accessible presentation, which you did a really good job. And I appreciated this very much because, as you know, I'm far away from your field of expertise. So I don't know much about signal processing. So I will ask you 1 or 2 questions, probably born out of naivety, but probably also a little bit provocative. See whether I can get you out of your comfort zone, and which, of course, I would enjoy. Let's see. So the first question is, if I look at the signals you presented of a seizure, here on the left-hand side in your logo here, they are blatantly obvious compared to a normal EEG recording. So why actually do you need such a elaborate, complicated filtering procedure to identify them? Would a simple FFT algorithm not be sufficient?
So for generalized absence seizures, one of the algorithms that was being compared which I'm going to try and pull up on the screen, was indeed based on wavelet decomposition, but wavelet decomposition is another way of doing a frequency representation of the data, or splitting it into different frequencies. That's the wavelet algorithm that you have right here at the bottom, and which is severely outperformed by both the algorithm that I'm proposing and by the SVM that Jonas and colleagues have actually proposed. The reason is, if you just limit yourself to some simple features, there will be artifacts that will have characteristics which very much match what you have in your epileptic activity. And so what you need is something that does distinguish between these artifacts which can present characteristics which are similar to the seizures and between your seizures. Those could be chewing artifacts, those could be tapping movement. And so it is indeed not between the background EEG that you're trying to distinguish and between the seizures. That is, you could even just do it on power and you would probably get very far with that. But you're trying to do it with events which do share more characteristics with your signal. And that is why actually the algorithms that I do, even though to simplify in this work I said they distinguish between seizures and non-seizures, what they actually do is they distinguish between seizures and what I call interferers. So events that have got characteristics that could look like an epileptic seizure, but which are actually not seizures.
Okay, now following on from that, you mentioned in your presentation a few times that your algorithms outperform other existing algorithm in terms of the required computational power you need for that. And again, my question is, why is this important? But because we have very powerful computers carrying around with us in form of mobile phones. Is this really a bottleneck, this computational power or resources you need?
And so it very much depends what you want to use the algorithm for. And in many cases, it will actually not be a bottleneck. If the main task is to do just a follow-up of patients where you want to have an accurate seizure diary, know how many seizures they have, you don't really care about being real time. You just need to record it, yet you can send it to a very powerful computer and get satisfying results. And that is why wearable EEG does exist nowadays. What we want to be able to do that real time. If you want to do that real time, you do get into power constraints. And there, the solution you were proposing was to say, for example, couldn't you let the smartphone do all the computation? If you do that, then you need to transmit all the data. We're talking about several channels, all sampled at 250 hertz, often in 4-byte variables, and continuous streaming would not allow to do very long-term EEG monitoring. You would actually very quickly run out of battery if all of them had to continuously stream data.
Okay,
so,
but I could build an ASIC to do the sort of edge computing concept where you do the signal processing really at or close to the location of the electrodes as well.
And so that indeed is what we need. What we need is some of the computing to happen on the nodes. The algorithms I propose use pretty standard multiply accumulate units or microcontrollers or whatever to do those operations. I could imagine some specialized algorithms could be used to run on some specialized hardware. And actually one of the jury members, David Atienza, which is not here, that is what his work focuses on. How do you build specific hardware for specific algorithms?
Okay, so talking my last question, talking about hardware, you require a lot of hardware if you demonstrate with the monkey here. Where do you see in the hardware chain is the limitation of the current state of the art?
In my experience, the limitation is related to electrode technology. Electrode technology that I have used throughout my thesis has been wet electrodes, which have got a tendency to dry out and which are, in all of my work, placed by a specialist, an EEG technician, or sometimes a nurse, depending on the institute. I don't have yet, that I have used, EEG electrodes that would just allow a patient to just run it at home. It's not to say it doesn't exist, and to some extent, Byteflies is doing that, but I do feel there is still some work that needs to happen in the electrode field to do long-term EEG recordings in a home environment.
So if you used dry electrodes, then what is the limit there then?
At this point, I have not seen or used myself a dry electrode which is stable enough over time, because even if the dry electrode doesn't fall off, It still does have some limitations in terms of how well is the contact established. Can you maintain a stable connection? Is this changed when you have perspiration or sweat? Or does this impedance stay stable over time? So dry electrodes should offer some help in that they would remove the drying of the electrodes. They still need to be a stable electrode.
Okay, good. So I failed. I didn't get you out of
No,
your
you did, you did.
comfort zone.
Or
Thank you very much.
Thank you, Jonathan, for the nice presentation. Can you give me a definition of an absence seizure?
I hope I can. An absence seizure is a generalized seizure which incurs a loss of awareness. And I think the definition is a seizure which has got a spike wave discharge of between 2.5 hertz to 4.5 hertz.
And why have you used, or do we use, a 3-second spike and wave discharge?
So the reason we use 3 seconds is that very short bursts of activity often don't have a clinical correlate. The clinical correlate is a test where you ask the patient, for example, I think some of the tests are related to driving in lanes, and you would submit someone to a car simulator, you would move his car in a different lane, and you would check if he could then get back to the same lane. What we observed is that for very short duration seizures, patients are still able to perform many of those tasks. But for seizures which are more than 3 seconds, there is a clinical correlate and they are no longer able to perform a cognitive task.
So some discharge of 3 seconds are not absences, some are. Is that correct?
So what I have been answering, but it is possible that I am getting slightly muddled up in definitions, is that an absence seizure is epileptic activity of more than 3 seconds, and that something which is sub 3 seconds would be subclinical and wouldn't be called an absence seizure, but would be called an epileptiform discharge.
Okay. Any idea why some absences occur with a very short discharge and others only after a longer discharge?
In my understanding, but again, I'm not a specialist on that, I do imagine that it is related to some dynamics in the brain and that there is some network configuration that would stop the seizure from continuing. I suppose the same mechanisms that stop a seizure of continuing after 10 seconds.
Okay. Can you tell me in what epilepsy syndromes you see typical absences?
So you see them in juvenile absence epilepsy and in childhood absence epilepsy.
Okay. And the ones in your study, which syndrome did they have?
If I remember correctly, they were juvenile absence epilepsy, which are the seizures that often continue in an adult population rather than stop when you are a teenager.
Okay. Now, in your title is signal processing methods for home monitoring. The problem is the signals you used are hospital-based.
Not all of them. In the first study, we sent patients home and we did 24 hours of recording in a home environment. But indeed, one of the limitations of this whole study is that many of the signals were recorded in a hospital environment, and we know that signals in a hospital environment are much cleaner, contain way less artifacts, and so some of the results we find, for example, in the miniaturization limits, it would be possible, we would actually need more than the minimum distance and the minimum number of nodes to be able to circumvent problems such as one electrode dropping out or one node dropping out.
Okay. Then in the absence detection algorithm, you argue that online should be okay, and then the question was already asked that you have false positives, and do you know what patients find acceptable to get as false positives for an alarm-giving system?
For an alarm-giving system, I think there had been a study by UCB to ask patients what they would find as acceptable. And if I remember that study correctly, there was even a difference between what parents would relate to acceptable and what patients themselves would relate to acceptable. If I remember correctly, parents were willing to accept a fairly high alarm rate of, I would say out of the top of my head, close to 10 false alarms per day. But I don't have that study in my mind, fresh in my mind.
Your device would be in the back of the room after 2 days. So they say 1 a week.
1 a week, they say, okay.
What implication would that have for your system?
When we were using 10 channels with my algorithm, we were at 0.5 false positives per day. So that would be 2 false positives, or approximately a week, 2 to 3 a week.
Okay, thank you. And then my final question, I've always been intrigued by your first idea of these wireless electrodes, which could be stuck on the head, would measure independently from each other. Do these exist?
Well, they do exist in that it's just a choice of how you place your connections. So you could use a bitefly sensor dot, and you could place 2 electrodes very close by to each other. There has been an American project, Epilogue, which has also which also is working on a wireless EEG sensor network. To some extent, they are in early development.
Okay, but then you still have wires with the sensor dot?
Well, it depends. I mean, in how biteflies uses them nowadays, indeed, there are wires and they are measuring across the scalp on different locations. You could imagine this technology being used differently. It is not something that industry is really doing.
Okay, and so could you briefly explain again what your last findings would be to help this concept?
So
you have the wireless electrodes, right? In my mind, I would give some electrodes to the patients and stick them on the head. Your findings, what would you conclude from that?
So what my findings are, my findings also are that you better place them at given locations depending on the seizure type that you're trying to measure or the spikes that you're trying to measure. Mm-hmm. So the question is slightly more complex than what I say, where I say you can just have glue electrodes which are placed wherever. And for example, I do not distinguish between scalp and between hairy part or non-hairy and hairy parts of the scalp. So I don't really know of electrode technology nowadays that would make it easy for a patient to touch an electrode on a hairy part of the scalp at a short distance and still get a stable connection. But I'm not sure I answered all your question.
Partly. It's okay. Thank you.
Hi, Jonathan. Thanks for the presentation. It was very, very clear. Thank you also for all the interesting discussions over the years, especially the mathematical ones that definitely kept me on my toes. Couple of questions. So, and I think actually Professor Van Huffel asked a similar type question in your preliminary defense, but I want to ask it again because I'm looking for a different answer. In the setup of your real-time absence detection algorithm, you discuss needing 40 minutes of data to identify your peak interferers. Can you think or can you discuss the situations where that would fail?
Yeah, and so the whole question here is that we are training algorithms. These algorithms are based on example data. And as I said, they're based on example seizures, but they're also based on examples of interference or of non-seizures. The question here is, in my work, I've often been using 40 minutes of examples of non-seizure data that has got high power. Why would that fail? It would fail because one of the configurations that you're measuring in the home environment would be different from the one you would get in your 40 minutes of data. So in my study, I was lucky that actually how I did that, it was all from home EEG monitoring. And so I could assume that it was home EEG. If I had trained that on a hospital data set and then just applied that on a home data set, it would have failed in many cases. I remember seeing one specific failure in my algorithm, which was someone that took the car and you had some very rhythmic vibrations from just the car. And I'm doing some cross-validation, so I'm switching out who I'm using as testing and training. If you had some of the car movement that was in the training, you would be pretty much okay in the testing phase. If you didn't have any of it, all those events would be marked as false positives, and it would increase the number of false positives dramatically.
How would you propose solving it?
I think that would be in some algorithms that do acquire more data over time and do acquire or have got some adaptation in the weights over time. So I don't think there is a universal way of solving it if you only have access to, let's say, 24 hours of recording. If over time your data set did grow because you have had access to more and more recordings, and that you could have a component that was maybe patient-specific and maybe a part of the component that was patient-independent, you could have more and more examples of real-world artifacts which you had not recorded in that specific patient. And so one of the things I had done there was, for example, to say, let's use the seizure pattern of that given patient, but let's use the interference pattern of the pool of all patients.
Okay. that actually provides the perfect segue to my second question. So in that same chapter, you talk about the fact that your false positives increase 12-fold if you use the non-specific version, non-patient specific version of your algorithm compared to the specific version. And then in the discussion of, I believe, that same chapter, I would need to check, you also mentioned that one of the main advantages of your algorithm is that you don't need a lot of training data, right? Which I agree with. Don't these two things cancel each other out, though? The fact that you don't need a lot of training data, okay, great. But you do need the patient specificity in order, as Professor Van Paassen already pointed out, to get to a false positive level that is maybe acceptable in the real world.
So what you're having here as a mechanism is that the algorithm itself, in order to be computational feasible in a wireless EEG sensor network, uses very little parameters. The parameters are the filter weights. And you do not find with this algorithm some filter weights which are just adapted to the whole generalized absence seizure population, and which does get enough to distinguish these spike wave discharges because it's compressed into too little data. And so that is why you do get much better performance of this algorithm if you have some data from that patient. And when I'm talking about some data, I am specifically talking about some seizure data.
So for that same problem, talking about the specific versus non-specific version, and of course, what you did during your PhD was academic, or primarily academic, but it was a Bakeland mandate, meaning industry-academia collaboration, and before you were working full-time at Byfly. So you definitely have had exposure to how products are developed in the real world, how it's very different from how things are developed in academia often, especially since we're dealing with medical devices and patients, and there's a lot of regulation involved, right? Am I making you nervous? If you think about a patient-specific algorithm, that means that you're modifying your algorithm after, well, you're modifying the version that you maybe got regulatory approval for, that you actually validated. How would you deal with that from a patient safety point of view?
Yep. So forward to that, I am not yet an expert in medical regulation, and so I don't know yet well enough what adaptive algorithms, how they can be used in medical field, because I do suspect they can be used to some extent, but I don't know the ins and outs of it. I do believe it is more complicated, and so as an easy regulatory pathway, what you would want to do is you would have an algorithm that doesn't change. And by the way, here I'm talking about wireless EEG sensor networks and real-time seizure detection. There are many other tasks that we first need to solve in industry, if we're talking about industry and not academia, before we actually start using these real-time absence seizure detections. And so the first thing I would do in industry is first get an algorithm that does not run real-time, that does not run specifically with a limited computing power, but is used mostly to do picking up and being able to say accurately, we are able to detect these seizures. We are actually still missing in the field, being academia or industry, we are still missing a big, good comprehensive data set of data collected outside of the hospital. We are always basing that on very small, usually single center studies.
But assume that you have something that works really, really well and you would want to start testing it in the real world, and you do it in a regulatory compliant way. We don't need to think about the details of how we do that, but assume that it is the case. If you think about how you would safeguard patient safety, how would you approach it?
So the safeguarding of patient safety is evaluating what is the impact of our detections on what you would be doing on the patient. And so it is very much going to fall on what do you do with an alarm. In most cases, or in the first cases, an alarm would be used to call for help and would be something that could be disabled by the patient himself in case it was a false alarm. So in the very first instances of these algorithms that would be deployed, there probably is quite little risk in providing some false alarms, such that you probably have more risk of not providing an alarm than of providing an alarm. Of course, there are user compliance issues, and you would not be able to provide too many alarms for the users to still be using it, but you would probably want to veer towards over-detecting than under-detecting. When I talked about abortive seizure medication, that could be given real time in case of an absence seizure that was detected, that is very far-fetched. That is not where we are today.
All right. I have one final question. So on the topic of your of variable selection, so at some point, I think in your discussion, you argued that channel selection is an essential method for wearable systems because patients don't want to reduce the number of electrodes they have on their head as much as possible, which of course from a usability point of view, I fully agree with. But if you're thinking about trying to optimize a set of electrodes for either specific seizure types or even on an individual patient-to-patient basis, versus trying to come up with a limited but optimal set that tries to cover many, many cases as well as possible. Obviously not perfect in all conditions, but as well as we can reasonably achieve. What would be your preferred approach?
Between a generalized setup that works across all patients and a patient-specific setup?
Yes.
So if you are going to limit strongly the number of electrodes, you will not get away without a patient-specific setup if you don't limit the type of seizures or the type of patients that you're targeting. Mm-hmm. So for example, you wouldn't be able to just say, we do focal seizure detection, that we place 2 electrodes, and in all cases it always works, because the focal seizures only originate from one part of the brain, and you will not see them on very distant channels. So, I'm getting a bit lost in what the question was.
So the fact of the matter is that you made that argument in your discussion, in your thesis. I believe it's in the paper too. But the statement is not very well supported by evidence, because you have not had a chance to actually test these 2 conditions against each other, right? So it's speculative that the patient-specific version would work better. But do you have actual evidence or insights from the work that you've done that would be the case based on data?
So I can't remember actually running it, but I'm convinced that if you were to run a generic condition on just all epilepsy patients, you would not get good results, and you would be able to show a huge increase of seizure detection performance if you're doing a per patient selection of where the electrodes were. There's a way to circumvent that, which is to say, well, let's be more specific in the type of seizures that we're targeting. And at one point, when you are very specific in the type of seizures that you're targeting, for example, saying, we only look after temporal lobe epilepsy, well, then you can use a generic setup. You're not really using a generic setup. You're using a setup for temporal lobe epilepsy. And that is done by a human expert, not done by the algorithm. And that's one of the things that we did not publish because we didn't find meaningful results in it, was that actually human experts are very, very good at telling you where should you place your electrodes if you know the type of seizures and you know the seizure population.
All right, thank you.
Okay, thank you, Jonathan. Very nice presentation. I really enjoyed it. I will start maybe with the 2 questions that we received from David Atienza, who couldn't make it here today. So his first question is the following. I'll just read what he wrote. In your PhD thesis, chapter 2, the key contribution is a fully automated seizure detection algorithm designed to run on a microcontroller targeting wearable EEG devices. An important effort has been done to make the system robust against noise, but if you have the option to have multiple biosignals, so not only EEG, can they help you to remove that noise? And if yes, which ones can you consider as interesting ones to add to your wearable EEG system?
Yeah, that's a very good remark. And in my work, I'm only using EEG, which is a pretty actually difficult signal to acquire. There are other biological signals that do also vary during seizures. And those, for example, in seizures which have a movement component, could be EMG, accelerometer, or sometimes heart rate based. Those biological signals are signals that would make sense to measure in many cases, and sometimes to measure the dynamics of the seizure itself, but sometimes also to measure the dynamics of noise or of interferers. And movement, for example, will often correlate with artifacts on the EEG and can be used as a further improvement to the algorithm. In the framework I used, we would have to find a way of combining these signals of different modalities or combining classifiers of these different modalities. So it's not a straightforward implementation of just adding an extra channel, but it could be used.
Okay, thank you. I'm sure he would be very happy with that answer. And then his second question is, in the complete thesis, the key hypothesis is to guarantee the proper behavior of the algorithms. No, sorry, I misread. The key hypothesis to guarantee the proper behavior of the algorithms is the fact that signals are stationary. Yeah. However, we know that this is not the case in many real-life cases of input signals with wearables. So if you would have to redo this thesis or do another thesis, I guess what he means is if you would do a postdoc in Switzerland on the context of non-stationary EEG signals, how would you approach that?
So I think it's one of the things I did suggest in future work. We would need to have some evolving algorithms. That would be future work. I believe that the first step is indeed to have stationary algorithms. Evolving algorithms would periodically remeasure some of the statistics of the signal to recompute a filter dynamically. For example, in case of losing one electrode or bad impedance of an electrode.
Yeah, and maybe I can add a follow-up question then. So in your case, you, in your second chapter, you have a noise covariance matrix and then a seizure-related covariance matrix. You could say we can adapt these covariance matrices with the data that you measure over time, but you don't have the labels in that case. So how would you approach that?
So it indeed remains a research question, so there's not a trivial answer to it. One of the ways of doing would be to do some real-time labeling, classification, and to use some of the samples that you are very sure of their label and use those in the recomputation and not use samples which are close to the boundary where you have some very strong uncertainty if your decision was a correct one. The tricky thing is you would have to see how these algorithms do evolve and do they still converge to a solution that makes sense, given that you're now training on unlabeled data. And there is a risk that they do converge to solutions that no longer make sense.
Okay, thank you. And then I had two more questions. So my first one is, in the original Bakeland proposal, I think the word distributed was there in the title, and we kind of discarded that along the way. But do you, at this moment, do you still think that including distributed algorithms in this type of context of EEG, EEG-based seizure detection, whether that's still beneficial? Is it needed? Is it a nice to have? Or would you say we actually don't need it?
So I would say it's required, and we can ask why we didn't go in it, because there's a finite amount of work that can go in a PhD. And so we did not get to the distributed step. We do have colleagues working on it, on the distributed aspect. And the reason you need distributed is that it's the question that Michael was asking, which is to say, what if you just had a smartphone that was doing all the processing? If you don't have some distributed processing, you need to transmit all of the data. And so to be able to monitor long-term with small devices, you do need a way of compressing the data along the way. And that's what you would do with a distributed implementation. And there's work to be done, because in the work that we are doing now, we only do compression of the number of channels. So we, for example, say one channel can maybe only communicate to its neighbor, which will communicate to its neighbor, and so on, instead of just communicating to the whole network of broadcasting. That is compression in the channel domain. We're not yet doing any channel compression in the time domain, which might also be required if we wanted to run these systems for a long period of time.
Okay, thank you. And then my last question is about the last chapter where you want to analyze the miniaturization limits of EEG. And there we worked on a data set which contained interictal spikes, and we used a spike detection type of algorithm to figure out what these miniaturization limits are. And that was because we didn't have seizure data with such high density EEG, which we needed for this study. So my question is, do you believe that the results that you obtained in this chapter can be extrapolated for seizure detection algorithms instead of spike detection algorithms? Or would we really need a high density seizure data set in order to...
So there are two limitations in this study if it was to be applied to an epilepsy data set. One of it is that this was recorded during very clean recordings of 2 hours in the hospital environment. And all of this work should be in a wearable environment or in a mobile environment where you do expect the data quality to be way lesser. This would have to be repeated or would have to be gathered in larger studies before it could be used, especially for regulatory purposes. But I would not be confident sending just the findings of this study in a home environment and just believing it will work. The second thing is more positive, is that spikes are much smaller power events than epileptic seizures. And so the limits that we found here are probably too strict if you had to do, for example, absence seizure detection, which is an easier task than spike detection. So again, the findings can't be taken just as the same numbers, but it does give an idea of how do these signals evolve across number of channels and across distance. It does give some indication of what guidelines you would need of your amplifier to do spike detection. Spike detection on its own is also a relevant task, and current work that is being done to do seizure prediction is often using spike rate as one of the variables that is used to do seizure forecasting or prediction. But indeed, for seizure detection, miniaturization limits would have to be re-evaluated.
Okay, thank you very much. I'm satisfied with that answer.
Thank you. Are there any questions or comments from the audience?
And I very much welcome questions. This is the moment to ask them.
If there are none, we will retire for deliberation. Dames en heren, ladies and gentlemen, geachte collega's, dear colleagues, ik geef u kennis van de uitslag van de beraadslaging van de examencommissie aangesteld voor de proef van dokter in de ingenieurswetenschappen. De heer Jonathan Dam heeft aan de faculteit een proefschrift voorgelegd, handelend over Signal Processing Methods for Home Monitoring of People with Epilepsy with a Network of Wearable EEG Sensors. In het Nederlands, signaalverwerkingsmethoden voor thuismonitoring van mensen met epilepsies met een netwerk van draagbare EEG-sensoren. En dit tot het verkrijgen van de graad van dokter in de ingenieurswetenschappen. En hij heeft dit proefschrift in een openbare zitting voor de examencommissie verdedigd. De examencommissie heeft vastgesteld dat zowel aan de wettelijke en decretale bepalingen als aan de voorschriften van het universiteitsreglement ter zake werd voldaan. Na beraadslaging verklaart de examencommissie dat de heer Jonathan Dam voldaan heeft aan alle eisen voor de proef en de graad van dokter in de ingenieurswetenschappen behaalt. Bijgevolg, en in naam van de rector van de KU Leuven, verleen ik u de graad van dokter in de ingenieurswetenschappen richting elektrotechniek. Now the most important sentences in English. Mr. Jonathan Dan, the examination board has concluded that you have fulfilled all the requirements laid down in the university regulations for the doctoral examination. By obtaining the doctoral degree, you commit yourself to act in accordance with the basic principles of research integrity, being reliability, honesty, respect, and accountability. Therefore, on behalf of the Rector of the KU Leuven, I confer upon you the degree of Doctor of Engineering Science, PhD in Electrical Engineering. Congratulations. De zitting is gesloten. This closes the session. Now there is still an end to this. You can sit down now. And the promoter will say a few words to the new doctor.
Good afternoon, dear Jonathan, or should I say Dr. Dan from now on. Let me start with congratulating you with your new title of Doctor in Engineering Science, also in name of your two co-supervisors, so Wim and Ben. Congratulations with this nice thesis work and the nice presentation you gave today. I would like to start with thanking all the jury members for assessing Jonathan's thesis, giving him a hard time with nasty questions. So thank you, Sabine. Thank you, Michael. Thank you, David and Jonas. I hope you can hear me. So Jonas was actually planning to be here today, but his flight got cancelled this morning, unfortunately. And of course, a big thank you for our chair, Yves Willems. Jonathan, I think we first met, if I remember correctly, during one of the kickoff meetings of the CZIT project, which was a joint project between KU Leuven, UZ Leuven, where also Wim was involved, and Sabine as well, UCB, Pili Pili, and then of course Byteflies, with the aim to develop a wearable EEG sensor for seizure detection in the home environment. You and I had a chat during one of the breaks in the meeting, and you immediately came across as a very enthusiastic, light-hearted, and motivated person. And sometime later, you contacted me with a message that you would be interested in doing a PhD in our group while staying on board with Byteflies at the same time. So we decided to apply for a Bakeland grant on the topic of signal processing methods for seizure detection in EEG sensor networks. And you wrote a nice project proposal, and you apparently also made a good impression during the interview for the Bakeland panel, as you were awarded with this 4-year scholarship to do a PhD. So I was very happy to welcome you at Biomed. And during your time with us, you became well integrated and appreciated within the team, even though you spent part of your time at Byteflies. So I really appreciated your regular presence in the office, which really made you part of the team here. And I did not take that for granted, as I've noticed that this is not often the case for Bakeland PhDs, where the PhD researcher often spends the majority of the time at the company's premises. And that was certainly not the case with you. You were often at the office with us, and I had the impression you also really felt at home with us, which is something I realized the day that I saw you walking shoeless in the office. Although you sometimes come across as a bit chaotic, sometimes, somehow you could pull that off and compensate for it with your charm and enthusiasm. It was a delight to work together with you these past 4 years and to be a witness of all the changes and sometimes drastic changes in your hairstyles over these years. So from long hair to short hair to long hair again, with a man bun, without a man bun, with a mustache, without a mustache, etc. Jonathan, you really are an all-rounder with not only a very diverse appearance and hairstyle, but also with a very diverse skill set, which really was an asset for us. You can work with advanced signal processing methods. You can conduct EEG experiments, validate and test new EEG technology, even on monkeys apparently. And you program with ease, you set up a remote server, and you even find your way around analog electronic circuits. I heard from your co-promoter, Ben, that this was also the case for your work at Byteflies, where you were recruited as a signal processing engineer, but quickly had to transform yourself to a firmware engineer. So this is a really remarkable and rare skill. At the same time, you have always been very approachable and willing to help out with your diverse skill set, even if it did not directly benefit your own research, like all the support you gave for the design of the ERC sensors. And I would like to also thank you for that. You also took a lot of initiative to push your project forward and to find collaborations with other labs. You developed a user interface for our collaborators in the hospital with Wim to more efficiently screen long-term EEG recordings for absence seizures. And you got in touch with Professor Paulson in Copenhagen to get your hands on some very interesting high-density EEG data sets that we could use to investigate these miniaturization effects. And in the preface of your thesis, you also mention that you draw your satisfaction from collaboration projects, bringing together people with different expertise, and that is really true. You helped out with the sensor node design in the ERC project, you collaborated in the Eureka Challenge, you like to collaborate with doctors, nurses, etc. And in that sense, I know that the whole COVID period was a difficult time for you. All of a sudden, we could not come to the office anymore. There were no chats with colleagues at the coffee machine or during lunch, no team building activities anymore. So this must have been especially difficult for someone like you who thrives on interactions and discussions with co-workers and who draws his satisfaction from pushing his Byteflies co-workers into the water during kayak trips. That's what I heard from a reliable source. Anyway, all joking aside, I realized these COVID lockdowns really had an impact on your motivation, but you persevered. And despite these difficult times during COVID, and even though we had to change routes a bit now and then, your PhD research actually went relatively smoothly. You can be very proud of what you have achieved in these 4 years, not only regarding your thesis research, but also all the other things you have done on the side at Byteflies and at Biomed. You are also very motivated in terms of science communication and the dissemination of the work that you do. You gave several guest lectures, co-organized the National Biomedical Day, and you presented your work at many scientific conferences, especially those where also the medical experts are present. So please continue these endeavors, as it is really important for us engineers to talk to potential end users of our technology, to explain what we do and what we can do in an understandable way, which is what you also did today. Over the years, you have also become well known within the team for being so extremely attached to your bike. Even to the extent that you typically would bring your bike with you into the office and place it next to your desk, as you could not miss it apparently. And when we went to Berlin for the big EMBC conference, you decided to leave a week earlier to go there by bike. And when you finally arrived in Berlin with your bike, even then the two of you remained inseparable. When we would go sightseeing with the whole Biomed delegation, your bike came with you everywhere you went in Berlin, even in every metro we took, no matter how crowded it was. At some point, I even thought you were going to present your poster at the conference with your bike next to you. I don't think that happened. Jonathan, it was a pleasure to have you in the team, and we will miss you. Please enjoy your well-deserved break during the next 2 months. I hope the weather will be great in Lausanne, such that you can go ski in the sun every day. As you mentioned, that was the plan for the next 2 months. And I wish you all the best with the next steps in your career as a postdoc in David's lab and with everything else. Jonathan, congratulations once again on your hard-earned PhD. I hope this is not a farewell, but just a goodbye, and all the best with whatever the future brings.
my role now is to invite you to the reception that we're going to do, but I will use the microphone to say a few extra words. All of what I've presented was my work and what I did, but as you can, of course, imagine, all this work is, of course, done in teams and with other people. And so I'll just use a few extra words now to just hugely, to express gratitude to everyone that has been involved. And so specifically, I'll start a bit earlier, and so I'll start, as Alex mentioned, with CSIT. Has been quite some time that now around Leuven and in Belgium, we have been looking at how we could measure people with epilepsy outside of the hospital environment, without even knowing to start with if it would be EEG or another modality. I was lucky to do that with Biteflies, and I was lucky to get collaborations with people from UZ Leuven and from KU Leuven. That is how this PhD started, where we realized that we were still missing some tools, and specifically EEG tools to measure people outside of the hospital, when at the time Biteflies did not yet have, and we could not really find commercial portable EEG sensors to do home monitoring. And so this was made possible thanks to WIM, thanks to the nurses, thanks to the other PhD students of WIM and other doctors, and of course thanks to the whole patients and the whole epilepsy community that has helped us. It was also made possible thanks to Biteflies, which has been working tremendously to improve healthcare, not just in epilepsy, but in other diseases, and has really pushed forward on how can we monitor people outside of the hospital. We're missing today the two Hanses, which made a lot of this possible, but they really were the drivers to get me here, but to get all of us where we are today with wearable sensors in general. And next to that, I of course want to thank the whole family and everyone that was support around me. I do of course thrive from interaction, from love around me that I feel, and I'm lucky enough to have many of it in the office and outside. And so just want to share an extra moment with you around a drink. So we can all walk there together. It's actually just next to, in the Arenberg Castle. We'll find it together.